Hi everyone, I'm Amar and I'll be presenting our work on enabling efficient policy-rich rate enforcement with phantom queues. This work is a joint collaboration with my colleagues Pritish, Ilyas, and Mike from Microsoft and my advisor Radhika from UIUC. Rate enforcement is common on today's networks. ISP's rate limit chooses traffic based on their subscription plan. Cellular service providers rate limit bandwidth-hungry video traffic to manage limited radio resources. Rate enforcement is also a basic tool used to actuate traffic engineering decisions in data centers and WANs. Network operators have following expectations from rate enforcement mechanisms. Firstly, they want rate enforcement to be effective at enforcing desired rate correctly. Minor deviations on shorter timescales are acceptable as long as the average enforced rate over longer timescale is correct. However, large bursts, especially orders of magnitudes larger than the desired rate, are unacceptable. Operators also desire the ability to implement rate sharing policies within the enforced rate. For example, being able to divide the rate of 10 Mbps between the active flows fairly. Other such policies include weighted fairness and prioritization. Lastly, we want to do this at a low cost so that our solution can scale to a large number of users, which is typical of ISPs, data centers, and cellular service providers. In summary, we're looking for a mechanism that is scalable and efficient, as well as good at enforcing rate correctly and supporting rich rate sharing policies. Let's see how well existing options meet these expectations. We have two options to do rate enforcement today: traffic shapers and traffic policers. Shapers buffer packets in queues and dequeues them at the desired rate. Incoming packets are stored in a queue, and over time, packets are dequeued from the queue at the given rate. It is easy to support rich rate sharing policies with shapers. We can use multiple queues to store packets instead of one, and then divide the rate R using some rate sharing policies between these queues. For example, we can do round robin to do fairness between flows. Similarly, we can also prioritize a flow by dequeuing from its queue whenever it's active. While shapers can support rich rate sharing policies, they are quite costly to implement. Here is what packet pipeline looks like for a shaper when implemented in software. On NQ, the shaper must process packets to classify them into shaper queues. NIC copies incoming batch of packets directly into the lower level cache of CPU, where CPU is able to process these packets quite quickly and thus consumes only 30 cycles per packet on average. At the time of DQ, the CPU must prepare a batch of packets to be DQ'd from all the shapers to transmit. Now, since DQ of a packet takes place after some time, the packets are no longer in the cache and must be fetched from the main memory to be processed. And this part of the shaper pipeline is quite slow and consumes about 300 cycles per packet on average. So, while shapers can be quite good at rate and policy enforcement, they are quite inefficient to implement. Let's explore the second option now. Policers work by filtering and dropping packets that are determined to be exceeding the desired rate. And this is done without buffering packets at all. Most policers are implemented using token buckets, where tokens are added to a bucket at the desired rate, and incoming packet must consume tokens to be transmitted. If there are no tokens in the bucket, the packet is dropped. Now, traffic policers do not need a DQ routine at all. The decision about transmitting or dropping packet is made at the time of NQ, and which we saw is quite efficient. Thus, traffic policers altogether only consume about 30 cycles per packet. Traffic policers have their own drawbacks though. Configuring a token bucket is challenging. You have to accept either under enforced rate, which means achieved rate is lower than the desired rate. Or if you try to fix that by choosing a different configuration, you get very large bursts, sometimes tens of times larger than the desired rate. And with a traditional policer, it is impossible to get both at the same time. Moreover, traditional policers do not support mechanisms to support rich rate sharing policies. Recent work called Fair Policer proposes a point solution to bring per flow fairness to the policer. It does so by attempting to divide token bucket capacity equally between the flows. However, it is not trivial to generalize this to other policies like weighted fairness and prioritization. So, unlike shapers, policers are efficient, but they are bad at doing rate enforcement and also don't support rich rate sharing policies. So in this work, we asked the question, can we even get a mechanism that is efficient, has good rate enforcement mechanisms, and is also policy rich? And our answer is yes. We present BCPQP, which stands for Burst Control Phantom Q Policy. It supports rich rate sharing policies like fairness and prioritization. It does correct and burst-free rate enforcement, reducing burst from 20 times the enforced rate to less than 2x. And all this at an efficiency comparable to police's and 7 times better than the shaper. We make two contributions with our work. We use phantom queues to augment policies to support rich rate sharing policies. And secondly, we design a novel burst control mechanism that avoid large bursts while also ensuring correct rate enforcement. We'll discuss how we can do policy-rich rate enforcement with policies first. We will start with the token bucket since as we saw earlier, it is quite efficient. But we will reimagine it to look like a phantom queue. A phantom queue is a simulation of a real queue. It has been used in the past as an active queue management mechanism. And in this work, we use phantom queue to enable policy-rich rate enforcement. Unlike real shaper queues, real packets are never stored in the phantom queue. Upon arrival of a packet, we immediately transmit the real packet and instead enqueue a phantom packet in the phantom queue. If phantom queue is full, we drop the incoming packet. And phantom queue is then dequeued at the rate R, but remember we are just dequeuing phantom packets. Actual packets were dequeued right at the time of enqueue. Phantom queues allow us to think about policies much more easily. Just like a shaper, we can use multiple phantom queues and divide rate R across queues using any rate sharing policy. For example, we can do round robin for fairness. We call such a system of phantom queues a phantom queue policy, or PQP for short. While they look identical, there is a fundamental difference between PQP and a shaper. For a packet coming in at time TE, PQP immediately transmits it and enqueues its phantom version in the queue. Thus, the real packet DQ time is same as the enqueue time with PQP. Shaper, on the other hand, buffers the real packet in the queue, and this packet is DQ'd some D time later. There are two implications of this. The good thing is that the absence of a DQ routine makes PQP as efficient as a traditional policy. But the bad news is that given this discrepancy in DQ time, there is some error in rate and policy enforcement. In this presentation, I'll focus on discussing error bounds on rate enforced by a system with single phantom queue. You can find details about a multi-queue PQ system in the paper. Given a phantom queue sized B bytes over any time window delta T, as long as the phantom queue occupancy does not go to 0, such that we do not waste any DQ opportunity, the enforced rate is bounded by the following relationship: R plus minus B over delta T, where again, B is the size of phantom queue in bytes. While the error can appear large on small time scales, as we increase the time window, the error amortizes and the enforced rate becomes closer to R. Here we can see how variation in a real Reno flows rate is contained within the theoretical bound. The error in enforced rate is also directly proportional to B, the size of phantom queue. The larger the size is, the larger the burst will be. There is also a hidden implication where a small b can also be problematic, as it can lead to phantom queue going empty too often, which results in under-enforcement. Now, so far we were discussing the case for a single phantom queue. The error also scales by the number of phantom queues in the PQP system. It is evident that how we configure phantom queue size has decisive implication on the performance of PQP system. So how should we size them? Should we size them by the BDP rule, where BDP is bandwidth delay product, as this BDP rule is used for shaper queues? Let's see how that works for a Reno flow when we try to enforce 10 Mbps. We see familiar sawtooths of Reno, and once we average out these sawtooths, we find that we're under-enforcing the rate. If we look at the phantom queue occupancy over time, we find that phantom queue occupancy is going to zero quite often. So what is happening here? A BTP-sized queue becomes full as soon as the flow exceeds 10 Mbps, causing packet drops and which forces Reno to halve its congestion window. And this is what results in underutilization. To ensure correct rate enforcement, we need to let flow overshoot 10 Mbps for a bit such that overshoot balances out the undershoot. This means that phantom queue should be sized equal to the size of the shaded region in this figure. And once we do calculation, this comes out to be in order of square of BTP in contrast to BTP-sized queues for shapers. And indeed, when we size phantom queues this way, we see that phantom queue occupancy is not going to zero, and that results in correct rate enforcement on average. But this comes at cost of enormous bursts, sometimes up to 20 times larger than the enforced rate. Now, while we use Reno as an example here, the problem exists with other protocols as well, for example, Cubic as well. So far, we have seen how phantom queues can make it easier to reason about policy-rich rate enforcement. We also discussed rate enforcement guarantees of PQP and discussed guidelines on how to size it. Now we will briefly discuss the burst control component of BCPQP. It should be noted that bursts usually happen when a flow is starting out and is usually in its exponential growth phase. When a flow in this state finds a large empty phantom queue, that is when we have burst. But once the phantom queue becomes full, flow enters steady state, either because of packet drops or exhausting the rate. After that, the flow has small acceptable overshoots, which we anyway need for correct rate enforcement, as we saw earlier, but no bursts. Our burst control mechanism monitors the incoming rate, which can be done very easily by maintaining one additional counter per packet per queue. We configure a safe rate threshold. If the incoming rate is within this threshold, no intervention is necessary. However, if the rate exceeds the threshold, we fill the phantom queue up with magic packets. Phantom queue becoming full forces the incoming rate to fall below R. We remove magic packets only when the flow's sending rate falls below a lower threshold. For example, when the flow stops sending data at all. You can find more details on how burst control mechanism generalizes to multi-queue system in the paper. So our burst control mechanism ensures that we do correct rate enforcement by sizing the phantom queues to be as large as required. However, it protects against burst by monitoring incoming rate and filling up the queues on the onset of the burst. So to summarize what we've discussed so far, we have shown how phantom queue policer can enable us to do rate enforcement with rich rate sharing policies. Additionally, our burst control mechanism ensures burst-free and correct rate enforcement. We implement BCPQP along with other baselines on Azure VM using Intel's DPDK. We run two more VMs, one running a TCP server, and the second one generating flows which are routed through the middlebox VM. We use Reno, Cubic, BPR, and Vegas as congestion control protocols for the flow. We also induce RTTs between 2 milliseconds and 50 milliseconds for these flows. And our flows are of different sizes, ranging from 10 kilobytes to 100 megabytes. We enforce rates of 1.5 to 200 Mbps, and we implement fairness between flows within each shaper or policer whenever it's possible. We measure CPU cycles spent per packet on the middle box VM and per flow throughput on the receiver VM. In the first result, we report quality of rate enforcement. We measure per aggregate throughput over 250 millisecond windows and plot the CDF here. The left plot will visualize average rate enforcement. The closer we are to the dotted line, the better is the quality of rate enforcement. The right plot shows the tail throughput. A shorter tail means smaller burst. Now, Shaper is quite precise with rate enforcement, and it also does not have any burst. Policer sized by BDP, on the other hand, is also able to do correct rate enforcement, even though there are variations in instantaneous rate, but they cancel each other out. But this large policer can cause a burst up to 20x the desired rate. A BDP-sized policer does not cause that burst, but it also under-enforces the rate. You can see how the graph for it is a bit left shifted. BCPQP is able to do correct rate enforcement while having no burst. We calculate fairness index over 250 milliseconds window for each aggregate and show the CDF here. This shows the quality of policy enforcement. Shapers, as we know, can do very precise policy enforcement while policers cannot. BCPQP is also able to do enforce fairness of same quality as Shaper. We already saw that Shapers are costlier to implement, but BCPQP is able to have efficiency 7x better than the Shaper when it comes to CPU cycles per packet. You can find more results in our paper, including comparison with other baselines and testing with real-world applications. To conclude, in our work, we've shown how you can do correct, policy-rich, and efficient rate enforcement simultaneously. This can enable several use cases for network operators. ISPs can give the ability to users to customize how their internet bandwidth is shared across their devices and applications at almost same cost as a policy. Cellular service providers can use BCPQP instead of Shapers to get burst-free rate enforcement for video traffic at a much lower cost. Data centers can use BCPQP to implement fine-grained policies like weighted fairness and prioritization when doing rate enforcement based on their TDCNs. With that, I would like to thank you for listening. Please reach out if you're interested in using BCPQP or have any questions. Thank you.